learned how to do. And this first part is just a little bit of introductory text. We have primarily dealt with things that are, one of the dimensions is way, way bigger than the other two. That something, we've had a very long X dimension and sort of a small Y and Z. A shaft, a beam, a wire is what we've primarily dealt with. In three-dimensional space, we've often simplified things to one of these internal reactions at a time. But really, when you slice a three-dimensional structure, you can have up to 6 reactions concurrent at the same place. You got 3 linear forces. We've called the normal one P, and 2 shears, a shear upwards, up and down, and a shear front to back. And then you've got 3 moments as well. And you've got, oh, I didn't bring my numeral again. But you've got bending the way we've thought about it. You've got bending front to back. And then the third one actually ends up being a torsion, a twist along the long axis. So when we now start thinking about things sort of in this combined loading or overall sense, like this structure here with this bird sitting on a light pole, like with that desk, it's got bending loading. If there was some wind load on the light pole, or a better, easier way to think about that is this sign. If you've got wind blowing on the sign, you've got shear at the connection point, like where the sign is concreted into the ground. You've got twist on the sign, and as well as a bending moment that would tend to want to make it bend over onto the ground. So by and large, we're still going to be dealing with these one-dimensional rods, beams, things like that. A very little bit we're going to deal with things that are one dimension is much smaller, meaning a plate. That you've got 2 dimensions this way, but a really thin dimension this way. Flat structures like that are plates. If you start curving them, then it's called a shell. The thing that we're going to deal with that is a pressure vessel, like an air tank or a propane tank. And we'll do this lab on pressure vessels. So that's sort of the intro of what we're talking about. The first thing to move forward is to make sure that we remember exactly what each of these different loading scenarios looks like and how we calculate the associated stresses with each of those. So if we have our beam and we've taken a section cut at an arbitrary place and we have axial loading, that guy is our internal force P. Again, remembering the sign convention, if it's away from the cut face, it's a tension. What kind of stress happens with that, Mr. Axman?
Normal stress.
It is normal stress. How do we calculate that, Mr. Taylor? That's right. And what does it look like? It looks constant over the whole surface. Sigma equals P over A. All right. If we have torsion, and we can draw this guy with, that's supposed to be a double arrow. A double arrow and an additional arrow to indicate the sense of it. What kind of stress does that guy result in? It's a shear stress, and it is along the face in the direction, and that's my attempt to show that it's smaller as you go towards the center. And what's the governing equation for that one, Mr. Beasley?
That would be V over A.
Nope, it's not. we've got an applied torque T. Which one is that, Oprah?
What? T over JG.
That's how to get the angle of twist. So very, very close. We don't want the angle of twist from an applied torque. We want the stress due to the torque. That's the one. That's the one. So we have a shear stress, and the maximum value is TC over J, where C is the distance from the center to the outer surface. Generally, at any location, T as a function of radius is TR over J. Tau as a function of radius, sorry. So the difference between the R and the C is just that the C is all the way at the outside. All right. So we got one normal stress, we got one shear stress. Now the transverse shear, that's like the trailer hitch. That is a shear along the face. And that results in what kind of stress? The shear force results in a shear stress. You know, how do I calculate that one? Can be, but not always. It's the specific one for any general location is VQ over IT. If I want an average value, you can do V over A. If I'm talking about the specific location-related one, I end up with what kind of stress distribution? Where's my max? Is it at the outside or in the middle? It's in the middle. How much is it at the outside? It's 0. And it's the same direction everywhere. Okay? And what distribution? How does it vary with Y? It's quadratic. So this stress distribution in Y, the max is at the neutral axis. So quadratic in Y. Two other special cases that we did the derivation for a rectangular cross section, tau max is 3/2 V over A, and for a circular, tau max is 4/3 V over A. So VQ over IT is never wrong for the shear stress at any given location. What is that Q thing? How do I calculate it? Which is more relevant to what you have to do this Thursday. It does. What's the formula, Brogdon? Anyone? Anyone? Yeah. So it's the area of the portion that would shear times the distance from the neutral axis of the structure to the centroid of the part that would shear. So instead of cluttering that up any more than it already is, oh, I have 0 markers. Oh well. So if that were your area that you had some sort of glue bond, it's that area that would move
times the distance from its center to the neutral axis. So a y bar and an a prime.
If you've got 1x4 stacked up or a T-joint or something that has that glue structure. And what would the thickness be in this case? It's the whole width. If you've got a T-bar or an I-beam or something like that, it's the width of what would be bonded.
All right. So now bending. What does it look like? If we take our section cut, if we draw our moment as a double arrow, that corresponds to
A bending moment in that direction. So would this one end up giving us a concave up or a concave down beam shape? This is my free cut.
concave up, so tension at the top or the bottom? Tension along the bottom, compression along the top. Okay, what does this result in? It results in normal stress that we calculate how? If we have a big... That's the one. And sigma max is a plus or minus MC over I. If you have a symmetric cross section. And what does this look like in cross section? How much normal stress do you have along the neutral axis? You have 0. Okay, and how much do you have, if we have this case, what did we say we had at the top, tension or compression? We have compression, so we have arrows going back towards the cut surface, which means we've got tension along the bottom, and that profile in Y is a linear profile.
So it's 0 along the neutral axis, maximum at the top and bottom when it's symmetric.
So this is linear in Y.
Shear stress is quadratic.
Normal stress due to bending is linear. So that right there is the stuff that needs to be in your brain for the exam, treated individually. You'll not have more than one going on at the same time. What we're going to start dealing with today is how to add them up
when you have multiple things, and this guy right here is very, very important.
We have 4 different cases, basically, where we have 2 things that result in normal stress and 2 things that result in shear stress. So normal stress and normal stress can add, and shear stress can add.
But you cannot add taus and sigmas. We will learn how to account for that
with this thing called an equivalent stress, but you cannot simply add the numbers from taus and sigmas together as is. They are not friends. You are not my friend. So how do we do problems like this? Example starts out with this guy. We have a square cross section, 120 millimeters square member loaded with a force of 10 kilonewtons. Find the maximum stress in this thing. So this thing has an eye bolt connected to the bottom that we've lashed a rope onto, and we're actually pulling on the eye bolt. So it's an off-center applied load. We know we're going to need some of these physical quantities, so we have a cross-section that looks like this. If we're given 120 millimeters, we know that that is actually 0.12 on a side. We know it's symmetric, so we've got a neutral axis in the middle. Area 0.12 squared ends up being 0.0144. Rectangular moment of inertia, 1/12 BH cubed, and that ends up being 1728 times 10 to the squiggle minus 6 meters to the fourth. What do? We have to do a statics problem. Now that we're moving into this, I'm cutting out a little bit of the detail. I will say that it is probably a good idea for the exam and for moving forward in these problems, refer to the sign conventions on page 4-4, because remembering which way the force is to be a positive shear or a positive bending moment is going to become more important as we're piling more things on top of each other. I'm going to take a section cut here in the middle, and for sake of ease, I'm actually going to look at the free body diagram of the right half, because we only have one applied force, so we can kind of take that shortcut. So we have, this is my right half, I've got this eye bolt, I've got 10,000 newtons. I know that this distance, I believe, was 0.1 meters. And I have my reference point O on the neutral axis of my cut section. So this is my section cut here. If I've made that section cut, you always assume your internal forces are positive, so you know if the sign matches, all is well. So I say I have an internal force P and an internal bending moment M, and then I do my statics problem. Sum of the forces in X minus P plus 10,000. We have a 10,000 Newton axial load, which you can see is going to cause this thing to be in tension. Okay. And then we sum our moments about our reference point O. And for that, let's go to Miss Arnold. And what's the, if we're talking about O as the reference point, what's the moment arm for that guy? What's the separation distance between my force? There we go. And is that going to tend to make it go positive or negative? If O is my reference point. Which way is it going to spin? Going to make us go that way. So that applied force is a plus 0.1 meters times 10,000 newtons. And then what else do we have? We have our internal moment, and that one's drawn globally as a minus m. So then that tells us that our internal moment is 1,000 Newton meters.
But according to our sign convention, the way I have that drawn is a positive bending moment because it's that right-hand face, which means it causes a concave up or smiley beam shape. And again, if you think about the real situation, if you think about if you pull on that from the bottom, what's it going to try and do? It will make it bend down this way. That's a frowny look. It's the sign conventions on that internal moment. Go back and review it. I think that might be what's making you frowny.
Well, you had minus M, but it's a positive, but it's because of O that you're.
Well, with respect, the internal moment is a positive bending moment, but this is drawn as a minus M in the right-hand rule roll. And again, that's the goofy thing with the moment sign convention. If you look at the left cut face, if you look at the right cut face, it matches. So, warning on that. Okay, so we have an axial load and we have a bending load. How do we figure out? We've got loads, internal reactions, now we want stresses. Stresses. What do we got going on? We got two things. We got bending stress. How do we calculate that? Stephanie. Minus my over I, or we know that the maximum, because this guy is symmetric, is either plus or minus, that you're going to have the same value. So I'm going to call this sigma bend, and I'm going to call it MC over I. We just figured out that this guy is 1,000 Newton meters. What's my C? Whoops, that was too much zoom. So yeah, the side is 0.12 meters, so therefore my distance to neutral axis has to be 0.06. And moment of inertia was that number that we did up there, times 10 to the minus 6 meters to the fourth. So our bending stress is 3.47 E6 Newton per meter squared, otherwise known as 3.47 megapascal. And that's going to be compressive or tensile here at the top. Okay, let's say we've got sigma bend here and sigma bend here with a magnitude of 3.47 megapascals. All right. What else do we have? What other kind of internal load do we have? We have axial. How do we get that guy? Plain old P over A. P was 10,000 newtons. The area is 0.0144 meters squared. So 6.944 E5, or 0.69 megapascals. All right. So give me another page. All right. So to sort of summarize what this looks like, hopefully without jumbling up that other drawing too much, I have compression at the top,
tension at the bottom because of bending stress. And with axial, what do I have all over the whole surface? Tension or compression? You have tension everywhere.
Does the tension that's all over the surface cancel out the compression?
Well, that's exactly the point that I was about to make. How big are these guys? How big is the sigma max from bending? That's 3.47 mega, right? So 3.47 mega. How big are these guys? They're the same everywhere, but they're only 0.69. So it doesn't quite cancel out. But overall, you end up with what? You end up with 3.47 minus about 0.7, so about 2.7 compressive at the top, and 3.47 plus 0.7, or 4.16 at the bottom. Does that make sense?
So would that be the final answer?
So your final answer, what's the worst case? The worst case is 4.16 megapascals of tensile normal stress at the bottom of the beam. Because these guys are opposite sign, they lessen the effect. They lessen the effect. All right. So I'm actually going to skip the chain link one and fast forward to the I-beam post one. All right. So sort of similar to me pushing down on this desk, we have an eccentric load on the top of a plate that's up on top of this I-beam. So this is the overview. So there's my plate, and I've got 10,000 pounds pressing down on the upper corner of this plate. So that's the point of load, point of application into the screen on a big view of the top plate. And I will point out that I meant to revise this and did not. This X and Y coordinate system is not consistent with the way that we've been talking about beams all along. What have we said? We've said X is along the beam, and then Y and Z are the other way. Well, X is across the plate, not along the beam. So just be mindful that this is not the same coordinate system that we've been dealing with. So our applied force is here. And what we want to figure out is, where is the worst case scenario? Well, what's this going to try and tend to do? You're offset in Y, so it's going to make a bending moment about X. It's also offset in X, so it's going to make a bending moment about Y. And it's also an axial force. So we've got three different things going on that we have to calculate and add up. And the scorekeeping gets a little more cumbersome, but that's the illustration that we're going to go through. So we've seen the beam tables before, where it gives various parameters. It gives distance, and it gives the moment of inertia about either one. So all of these quantities that we're going to need.
we know that this is a cantilever, so we know that the worst case scenario is going to be back at the connection point at the base. So like if we took a hacksaw and cut it off right at the concrete where it's connected, that's where our worst case will be. So if we say near the base, what are our internal reactions? And I'm going to do my best to draw a sliced cross-section of my I-beam. And so this is my that's not as bad as some have been. So what do we got going on if we have this section cut? We have a moment about our x-axis. We have a moment about our y-axis. And we also have straight downward this axial load. We know that the applied force F is 10,000. But we're actually going to remember that this I-beam has weight of its own pressing down on its support. So we're going to add that in, and we have to figure out what the numerical values of these are. So starting with the axial, so P is going to equal the applied force plus the weight of the beam itself. And a piece of trivia about this beam naming, that is a linear weight in pounds per foot. So it is 16 feet tall. So this is 10,000 pounds plus 16 feet times 54 pounds per foot. So we know that that has to be, that is 864, so we get 10,864 pounds.
And we know from the geometry of it that that's compressive. That's why I've gone ahead and drawn it down.
All right. How about our moment reactions? We've got a 10,000 pound force. What's the moment arm for the moment about the x-axis?
If I'm talking about what is the moment this way, what's the moment arm for that force? That's the 12. And the moment arm that would make it this way, moment about y, is the 10.
So coming back down, moment about x is our 10,000 pounds times 12, or 120,000 inch pounds, and our moment about y is 10,000 times our 10 inches. All right. So that is our internal reactions that are causing stresses. What kind of stresses do those cause? Normal, we've still got no shear. So both of these are causing bending stresses. How do we figure it out? Axial is plain old P over A. Where do we get our A, Brogdon? From the area of the beam, which is 15.8. So we've got our 10,864 pounds over, what was that number, 15 something? Thank you. 15.8 inches squared out of the beam table. That ends up being 688 psi. And that is in compression, so I'd throw the negative sign in there. How do we figure out our bending about X Cassiola?
Negative M I or negative M Y of
Do we know which way? It's a symmetric one. So I'm going to do the more general case. Instead of Y, I'm going to say plus or minus MC over I. What's my bending moment for that one? Let's go to Chance.
Okay. We got X. Either 120,000
Yeah. Yeah, where do we get that guy from? We go back to the geometry. No, it's the distance from the neutral axis out to the outside. So we go back to our beam diagram. And which one are we talking about? We're talking about bending about X, right?
Oh, the inside of it. That's what it's
Right. So not the plate, but the beam.
So 4.37. I'm reading the wrong number.
No, that's a fillet radius.
Would be half of the D.
Right.
Right.
So we want
10.9,
half
5.05.
of that guy.
So half of that guy, and I don't like math, so I'm just going to do that. And then the moment of inertia, we come back and we get it out of the same table. Which number do we want, Mr. Taylor? 303. That's right. So that is 303 inches to the fourth. So that number is plus or minus 2,000 psi. Now for bend about Y, we also have plus or minus MC over I with some different values. Miss Mitchell, what's that bending moment?
About Y is 100,000.
So that one's 100,000 here. What's my C Lakia? $10.03 divided by 2. Everybody see where that one came from? Okay, back up here on the drawing. We're talking about bending about Y this time. So what is that? That's the width. Width is that divided by 2. So this is 10.03 divided by 2. And what's my moment of inertia, Melissa? 103 out of the table. It's too far. 103 inches to the fourth. And so this ends up being plus or minus 4854 psi. All right. Now, I have laid mine out slightly differently than yours. I'm going to make a picture of what's going on at each one. So we had axial, what was that value? We had minus 688. What does that look like? That looks like it's the same everywhere. So that's going to look like compressive and equal over the whole cross section. All right. So now bending about X, that one was plus or minus 2,000. Okay, now which way is my neutral axis for bending about x? Is it along this way or along this way? Choice B, right? Okay, so that's my neutral axis for bending about x. And what does that look like? Do I need to be compressive or tensile on this face?
No, compressive. It's got to be compressive because that's where our load is.
Okay. Or let's go back and let's orient ourselves. If we come back up here, where is my loading? It's on plus x and plus y. Okay, and if we label these, we have A, B, C, and D. Okay, and if we come down and label our little cross sections, let's label those with A, B, and C, and D as well. So we would have A, B, C, and D. Okay, so the AB side needs to be the compressive side for bending about this axis. Is everybody with me on that now? Okay, so this guy is compressive everywhere. This guy is tensile. And how does it vary in here? It gets smaller. How much is it? The neutral axis is 0. And then a little bigger, a little bigger, a little bigger. Okay, that's kind of a bad drawing, but here you have minus 2,000, and over here you have plus 2,000. All right. Now for my bending about y, my value is plus or minus 4,854. My neutral axis this time is along the web. And what does this look like? At point A, am I tensile or compressive? Okay, which means I also have to be tensile here. Compressive here, and how does it change in between? It varies linearly. So now we're going to go to what I'm kind of calling the scorecard. From your drawings or your remembrance or whatever, what are the contributions at the corner A from axial? No, you don't. So what is the normal stress due to the axial loading at corner A? It's minus 688. You don't have that table.
No, I just screwed up the drawing.
Oh. I can make it a little smaller so maybe we can see. No, it's not going to be paginated right.
Oh, yeah, might be.
That might help. Can you still see the numbers over here?
I just didn't have the drawing.
All right, so what is my axial contribution at point B?
All the actuals should be the same thing.
That's right. So axial at point B is minus 688. Axial contribution at point C, minus 688. Axial contribution at D, minus 688. The axial stress is constant over the whole surface. All right. For bending about X, what do I have at corner A? I have minus 2,000. At B, minus 2,000. At C, plus 2, and at D, plus 2. And for Y, at A, I have plus 58, whatever that number is. At B, it's compressive. At C, it's tensile. And at D, it's compressive. So then you just add them up. So you end up with my previously prepared finished product. So where's my worst case?
Which is under the load point. Should stand to reason. So this has been 2 examples where all we have going on is normal stress to add up. Next time we will see what happens when we start having shear stress as well. So keep an eye out for your combined loading things.
Did you see that first page that has a vertical column on it again?
That guy?
Okay, I just need to see.
Yeah.
Okay.